Hello, welcome back. This is the video for the week 3 recap. As of recording, it's actually week 4, so a little bit of a delay. Still had to work on getting to the swing of things here. Um, so Schoology kind of shifted around and kind of reorganized where things are located. So we're moving on to the next unit as of this video. So the past week stuff it's in its own it's in its own folder in the unit 3 folder. So you'll see week 3 materials. In it, you'll find the agenda and the 3 things we worked on that week. In the overall folder, you'll also find the notebook I work out of, the presentation that I show you guys, as well as the textbook and a rubric for the assessment here. The new resources tab, or inside the resources tab now, is the new units, unit 4 textbook, as well as unit 4 presentation. We're not going into that today. This past week, week 3, I collected 3 things from you guys: the practice with the electron configuration, the lesson 2, as well as your weekly reflection. And as a reminder, if you have a 3 out of 5, 2 out of 5, 1 out of 5, you could always redo the parts of the assignment that are labeled missing or whatever, and try to get back to a 4 out of 5. Just remember, if it is turned in late, you're not getting a full score. That's just the deal there. And so you'll read that right there. So this week in class, we finished off lesson 2. We started off the notes on Monday. Actually, yeah, we partly started off the notes on Monday. Tuesday, I was out, so we had a substitute, and you were supposed to watch a periodic table video and fill out a form and get yourself started on the unit test, or part of the unit assessment at least. Wednesday, we went back to it, finished off the notes. On Thursday, we started up on lesson 3. Didn't have time to get started on the unit assessment on Friday, although people were asking questions, and I'll go over what I said back then. And so that's what this practice stuff was due. Lesson 2 was due, so let's get started here. Traditionally, you know what the drill is. If we had things to do that week, let's go through it. I'm going to go a little bit out of order. First, we'll just cover what you're supposed to have put into your notebook, and that there is the notes on nomenclature and 3D structures. So you know the drill. Copy and paste all of this into your notebook. What we do at the end of the unit, which is lesson 3. Open that guy up. Copy that, paste it into the notebook you have, and we work on this as a class. Now, Tuesday's assignment was a little bit special. It was a form you guys were to fill in, as well as a question to answer based off a video. I'm not going to show the video on YouTube, so click the links, fill out the forms, answer the questions. It's very difficult to mess that up, as you can see. All right. Now, let's kind of get started here. Practice assignment. So in reading your guys' reflections, I noticed a trend. A lot of you guys were still confused about electron configuration, and I understand it completely. We did kind of rush by that. And so to briefly go over the practice assignment that was due this past Friday, the first part of the question is fairly straightforward. If it burns a certain color, it has a certain level of energy associated to it. And what you're doing in this question is just ordering it, highest to lowest. For electron configuration, we're going to need that chart that is up above in the notes. But the end goal here is to set us up with the highest energy level and how many electrons are in that energy level. And so the way I've been explaining it, in a given energy level, you could have different types of orbits. So in energy level number 2, you could have an S orbit and a P orbit. Depending on what that orbit is, you could have 1 or 2 electrons or up to 6. And so if we take the aluminum, for example, we're going to have 3 energy levels. And inside the first energy level, we only have 1 type of orbit, and it's filled. So it's got 2 electrons. The expand the shell a little bit, you go to the second energy level, and you've got two different types of orbits. They're all filled, and so 2s2, 2p6. Next up, third energy level, the s orbits are filled, the p orbit, we're all in aluminum, so you just got one there. And so that's how you do electron configuration. You go through those energy levels. You could shorthand by just going to the previous one and just saying, all right, neon, you're looking pretty complete. Put the neon in brackets, and then just start off with 3s. Or if your element is like indium, you gotta put kryptonite. No, I forget that. Forget the KR. Pretty sure it's krypton. You put krypton in brackets, and then just start off with 5s, 4d, and then 5p. Super straightforward in that case. It's not necessarily that it is straightforward, it's just that that's all I'm asking for. Now, based on the highest energy level, you could find out the valence electrons. So aluminum, there's 2 electrons in the s orbit, 1 electron in the p orbit, it's got 3 valence electrons. And so that's 3 dots. When you're drawing these, there should only really be 2 dots per side. So top, bottom, left, right, 2 dots. If you end up putting dots in the, just like as if it's a triangle, it's not inaccurate, but later on down the line, it is going to confuse you and trip you up. So you want to build good habits. You want to fill in this chart, and this chart's really straightforward. Valence electrons, total number of electrons, atomic number. Those are straightforward enough. The biggest thing that might give you trouble is the number of neutrons, which is just your atomic mass subtracted from your subtracted by the atomic number. Now, lesson 2, briefly going over this, you want to have everything we did in class. So that's all the blue stuff filled in. There may be 2 questions that we did not do together in class, way down here, as to how does electronegativity compare to atomic radius? What about ionization energy? And to just see a quick comparison, you want to go to P table, electronegativity. I look at the pattern there, compare it to ionization, compare it to radius, right? So you just want to do a compare and contrast with those 3 topics. Next up, the other ones we had were properties of metals, metalloids, and nonmetals. We did this in lesson 1, so this is just more of a recap. But the big thing for this assignment is your own copy of the periodic table. This is the one I made with you guys during class. And you want something similar. The big things are the groups are highlighted. Yes. The groups are highlighted, and I've got arrows to show where the pattern for these 3 trends: atomic radius, ionization energy, and electronegativity. Those are the big things that I want: groups and the patterns. Originally, yours is blank, so fill yours in with the many draw tools that exist on Google Docs here. All right, so that takes us to nomenclature. Close that off. Now, as far as nomenclature goes, there's only one vocab word: polyatomic bond and polyatomic. To break that word down, think the word polygamy, polytheist, polynomial, more than one. And so if you have a polyatomic bond, you have a bond with more than one atom. So if you have H2O, the oxygen is bonded to 2 hydrogens. That's a polyatomic bond. We'll get to the rest later on here. Nomenclature, where we're at. Let's go to the presentation as well. Right around here. You're actually, I keep missing one. All right, there we go. All right, so ionic compounds. Ionic compounds are, I best describe them as greedy things. For an ionic compound, you have an electron that is completely taken over by another element. So you got 2 elements. One of them is very electronegative. You'll come in and just steal the electron from the other atom. And we have that image here. We have chlorine. very electronegative, maybe like a value of 3 on a scale of 4. And then sodium, not very electronegative at all, maybe a value of like 1. So chlorine is going to come in and just yoink, take the electron, which is fine by sodium. Go ahead and annotate this here. If you look at it, sodium, this electron is kind of acting like a pimple. Sodium wants to get rid of it. That way it could become stable and have a nice shell of 8 electrons. Chlorine, it's missing something here, right? And so it takes the electron, and now look at that. Chlorine is looking nice and stable also. And so the ionic compound is actually quite stable. Sodium and chlorine by themselves, they are not stable. They are very unstable. And so combine the two, you get a very stable compound. So we answer these questions here. If we look at calcium on the periodic table, you can determine how many ions it would form. And it's just the valence electron. A good rule of thumb, and it is just a rule of thumb. A good rule of thumb is if it's got 3 valence electrons or less, it's going to be giving up electrons. It's easier for these atoms just to give them up and then become stable the other way around. For elements like nitrogen, anything with 5 valence electrons and higher, they want to take electrons. They want to get to 8. The end goal for these atoms is to have an octet and be like helium, be like neon, be like argon. For the ones in the middle here, carbon and down, these will vary. They'll either give up electrons or take electrons. It depends on who they're bonding to. Typically, though, you're going to see them share. And we'll get into that in a second. So that's a good rule of thumb. So if we have calcium, calcium's got 2 valence electrons, which means it's going to give up 2 valence electrons. If we look at fluorine, it's got 7 valence electrons, meaning it just wants 1 more. So if calcium has 2 and fluorine has 1, well, what's going to happen is that a second fluorine is going to come in and try to take the other electron from calcium. And this is how you start to see molecules form. You have calcium fluoride. And in a crystal, in a compound, it's never going to be just 1 calcium, 2 fluorines. It's just an overall ratio, like baking a cake. You're not going to have the exact amount of flour. You're just going to have a recipe to follow, right? A ratio. So if you want to build a bigger cake, you could do that. Just multiply the ratio. All right. And here's what I said, just in text form. If you're in group 1, you're going to get a +1 charge. You're in group 2, a +2 charge. In group 13, a +3 charge. And then in group 14, +4, -4, it depends. All right. And so the question here is for aluminum. Aluminum is giving up electrons. Now, the issue with charges is, and I understand, it's a confusing thing. If aluminum gives up electrons, you might think to yourself, okay, aluminum gave up 3 electrons. It's -3. But that's not the case. These numbers here do not represent whether or not you have more or less of something, or if they do. They don't represent just that. They represent specifically the charge. And so if aluminum loses 3 electrons, that means electrons went away. And so this is actually a positive. So aluminum becomes more positive now, right? It had a center here, and it had some electrons around here, and these guys just skedaddled off. Skedaddled off, and now aluminum is just more positive. It's like leaving a bad relationship. And so aluminum is a positive ion. So had a little bit of practice with this in this chart here. So if you're in group 1, you got a +1 charge. Group 2, +2. Group 3, group 13, 3+, and then working our way backwards. Group 17, 1-, 16, 2-, 15, 3-, so on and so forth. Got a little bit more practice with this. And so as far as predicting things go, let's look at lithium and phosphorus. Phosphorus is down here with nitrogen, group 15, so it just wants 3 more electrons. Because this is the case, lithium, which only provides one, is not enough. And so 3 lithiums need to come together and bond with the 1 phosphorus. So you'll get lithium phosphide. Let's see. So to represent multiple lithiums, you have to do it in a subscript, Li3 with a 3 on the bottom. And charges are typically represented as a superscript, exponential. That's one thing I'll want to make sure you're aware of. And so when it comes to charges, you want to make sure they're balanced. With calcium and sulfur, 2 plus, 2 minus, they balance out. With aluminum, though, aluminum is 3 plus, oxygen is 2 minus. That doesn't balance. And so you want to make sure those charges cancel out. And so aluminum is doubled. You get a plus 6. Oxygen, you triple it. That's a 6 minus. And if we do that, now our charges are balanced, and we now have our chemical aluminum oxide. Cool. Okay, so I'm breezing through this right now because it is just a recap and not a 4 or 5 hour long video. Covalent compounds are our next type of atom here. So go back to here. For a covalent compound, these are compounds that share electrons, and they only happen if your electronegativities are samey, right? They're almost the same. And so with this, I'm choosing to use this image because it's bigger. With these atoms, let's go ahead and use the draw tool again. Hydrogen wants 1 more electron. If we got 1 more, it'd be nice and stable like helium. And so it's going to try to take carbon's electron. These guys' electronegativities are about 2.2 and about 2.5. And so they're very similar. So they'll share electrons. And so carbon will share 4 electrons with 4 different hydrogens. And this forms a very strong molecule called methane. And so these sticks here represent 2 electrons each. 2 go into hydrogen, and 2 also going to the carbon here. And so carbon is nice because it's got 8 electrons here. And hydrogen is happy because it's got 2 electrons also. And this works for pretty much most organic molecules. If you look at oxygen, oxygen has 6 electrons each. But luckily for oxygen, there's another oxygen nearby. And so these guys will form a bond. These electrons will form another bond, and you get a double bond. And so oxygen's got 2, 4, 6, and 8. So these oxygens are nice and steady with 8 electrons. This oxygen's nice and steady with 8 electrons. And this works out very well for people because, we breathe air. And next up, we have carbon tetrafluoride. This is the example. I chose to draw it out. We have fluorine with 7 electrons, carbon with 4. And so fluorine and carbon will share 2 electrons, like a weird custody thing. And that's a bond. Now fluorine's got 8. Carbon overall has 8. Everyone's steady. This image I stole from the internet. Well, I didn't steal it. It's a free use image. But the thing I don't like about it is that it does not show the electrons around fluorine. And at this stage of your learning, that's important to remember. Keep that in mind. Because when we start talking about shapes, this is an actual important thing. And so fluorine has got very negative electrons all around it. And so that brings us to Vesper theory. I really like this name, Vesper. I don't know why. I guess I'm a James Bond fan. But Vesper stands for valence shell electron pair repulsion. And so the idea here is nothing really too far-fetched. It's the idea that if something's negatively charged and another thing is negatively charged, those two things don't want to be near each other. And if the same thing, and if something's positively charged, same deal. And so this is how we decide how a molecule is going to end up looking. Take methane, for example. Methane, well, the carbon is slightly more electronegative. These hydrogens are very positive. Actually, no. The hydrogens are also negative. So overall, though, if we really wanted to see it, it's mostly positive. But at the end of the day, what we're saying here is that these guys want to be as far away from each other as possible. So we're going to get like a weird pyramid shape, a tetrahedral, if you will. And so with hydrogen, or with nitrogen with 5 electrons, let's draw them out here. Nitrogen has 5 electrons. 1, 2, 3, 4, 5. Hydrogen's got 1 each. And so you see the angle kind of gets smaller. It's a little bit smaller. So these electrons are really pushing these guys a little bit closer to each other. That's because these electrons are negatively charged. Negative, negative. They want to be really far away from each other. And with water, the gap becomes even smaller because we've got more electrons here. And that pushes these other electrons farther away from them. And so water ends up kind of looking like a V. This is actually very important because water is very polar. It's got very positive ends. It's got very negative ends. And so water is very, well, we'll get to polarity in a second. I'll stop for that. All right, let's move on here. All we were doing is just drawing these images out. I deleted a few, so make sure you don't do too much there. I don't like that at all. Let's go ahead and use that normal text. There you go. Okay, lesson 3. Finish this off on Monday, so great spot to start. We're going to complete the vocab, and we've already done that. The vocab is ionic bond, basically a bond that takes elements from one to another, creating ions, ionic. And it's got an electronegative difference between 1.7 to 0.3 or 3.3. Covalent bond, slightly less of a difference, electronegative from 0 to 1.7. And it's a bond that shares electrons. This is a bond that could be polar or non-polar. And actually, that's an important thing to include. Could be polar or non-polar. The molecule is just atoms bonded together. And H2O is a molecule. That's it. The metallic bond is just that. It's a bond created in metals using an electron C. And I'll talk about that in a second. Metallic bonds are responsible for metals' ability to conduct heat and electricity. All right, that was a real quick, just kind of forgot to pull that in there. Now, let's look. In lesson 3, we have this much assignment to do, and this is pretty much all you guys. So with this image, this is probably one of the best images you'll have here to figure out what kind of bonds you're looking at. And the type of bond that is created really does impact the properties of the chemical or the molecule that is also created. And so for number 2 here, you want to list these electronegative differences, right? Just on your own. See the image, list them out. That kind of mental feedback of just being able to do that will get you a lot more than just me talking to you again. Now, for this next one, number 3, I got 2 examples for you. We want to find out the electronegative difference between carbon and hydrogen. To do that, I look up P table, I look up electronegativity. There's carbon at 2.55. There's hydrogen at 2.2. We just subtract the 2. That's the electronegative difference. That's about 0.35. We look at the chart here, 0.35, but that's a slightly polar covalence. So that's our bond type. Which one's more electronegative? That's carbon. And so what's that compound? It's carbon-hydrogen. That's it. For carbon and sulfur, put the slightly more electronegative one up front. Sulfur at 2.58. Carbon at 2.55. This puts us at a non-polar covalent bond. And so the more electronegative atom in this case, it varies, right? Carbon, sulfur, it is sulfur. And so the way this compound is written, because they are sharing electrons and it's non-polar, you could just write it either or, carbon sulfur or sulfur carbon. Typically sulfur carbon is what you want, but I've seen it both ways. And so that's what you're doing. You're looking up the electronegative values of these chemicals on the table or on the charts I've given you. Look them up, subtract the values, figure out what kind of bond it is. This here is just an explanation for ionic bonds again. And it goes a little bit more in depth. And so we've talked about losing and gaining electrons. And if this happens, the thing that gained an electron is an anion. I always see the word onion there. And the one that lost an electron is positive. It becomes a cation. Again, I see the word caution now too. Thanks for that, students. And so all we're doing is we're just labeling who loses what. So if we look at sodium, sodium's got one valence electron, I'm just going to give it up. So sodium is our cation. Chlorine is our anion because it gained sodium's electron. All right, now let's just wrap this up. For number 5, we're talking about covalent bonds and ionic bonds, but more importantly, we're talking about how molecules made with covalent bonds, their strength versus an ionic bonds molecule strength. And so covalent bonds are very strong. They're interlinked and they're sharing. It's very hard to break a covalent bond. However, if you have one molecule made with covalent bonds and another molecule made with covalent bonds, they're not going to really be attracted to each other very well. And so ionic bonds do get attracted to each other very well. We'll get into this more in the next unit. And so you'll discover it requires less energy to melt a molecular compound with covalent bond than it does an ionic compound like salt. And so the attractive forces between individual molecules are stronger. The forces between molecules are stronger than between the ions. So it's like a guy with an adamantine skeleton and like a grip force of like 1 pound. That's your covalent bond. Really tough on the inside, really weak grip. An ionic bond is like a guy with brittle bone disease, but like a 500-pound grip strength, right? Really weak on the inside, but really sticks to other guys, other molecules. Here's our explanation for metallic bond. I'm not really going into it too much, but the general idea here is that we have atoms of metal just hanging out. And because they're so close to each other, these electrons can just kind of shift from one atom to the next relatively easily. And so if we ever have a current, these electrons move back and forth very nicely. The heat flows very nicely. The protons of these atoms are so close to each other, it's really easy to shape because of the electron seat. These atoms are relatively weak as far as the bond goes, but the molecule is very solid. All right, and so for most of this, you are doing this yourself. How are the different types of bonds similar and different? What are those different types of bonds? And how would you test conductivity, solubility, melting point? For this data sheet here, we did most of this together in class after watching a YouTube video of me performing the experiments. And so I'll just left that up. And then for number 3, watch the video and see how you are explaining this third one here. That takes us to the end here. It was a longer video, 30 minutes, but I do basically condense a week down into 30 minutes. Feel free to jump around. I do not mind. I make this for you guys. If no one watches it, no one watches it. It's fine. All right. Have a great rest of your day. Thank you. Bye-bye. And end the meeting now.